So we were talking about, I noticed all the presentation starts, the first word in my recording is so sorry about that. When you first start, that means I just started talking. Mosaic displays, so we're talking about multi-dimensional data, really two dimensions. This in a way, it's statistically, for a statistician, they may say it's two dimensions, but I think there's actually three if you put it in a table format. But the next two topics, this one and the next one, really cover some statistical anomalies when they, and visualization, where they relate to visualization. So for this one, has to deal with data, statistical data that's not completely independent. So here is what happened. Let's say one class, somebody took a count on how many people have black hair, brown hair, red hair, and blonde. And then also they look at eye color, green, hazel, blue, brown, and so forth. You can see the totals in there. And that's pretty much, for each category, you can have subcategories, and you have a bunch of subtotals, and then the final total number is 592 or so. So here is the first try. What if we display that data using area? So in other words, you see here that the area for people who have brown hair color, and is that blue? Blue eyes, that's kind of the area selected by that. So how do you go ahead and do that? You really have one or two ways. I don't know if they started horizontally or vertically first, but you look at your subtotals, and then you first divide the x-axis based on the subtotal. And so people with black hair get this much. Let me try and zoom in because I'm not seeing it clearly. So people with black hair, that's their subtotal. Brown hair, 286, red hair, and blonde hair. So you figure out where your subtotals end that way. Then you go on the y-axis and do the same thing. So brown hair people, there's 226. Blue-eyed people, 216. Or hazel. I guess what's the difference between hazel and green? Hazel and brown, that's what I'm asking. But, and then you have green eyes. So that picture may be, what's the other eye color? Yeah, there's a hazel eye color in there. So once we divide them like that, hopefully you get the right results. Well, it doesn't work. Here is, and I think I almost pointed the first one I went through. So if you do the calculations on the area for each rectangle, the total being 692, you look at the total, and then you look at, for example, this one that I specified, the area that's demonstrated by that rectangle that we see right there should be about 162 people. So that would be for people with brown hair and blue eyes. So 106. Or sorry, 160 something, 163. I moved the wrong way. Now here, if we look at hair color brown and blue eyes, there's only 84. How did that happen? And here is the problem. The problem is genetically, hair color and eye color are not completely independent. For example, here is an example of an independent variable, the temperature in this room and the height of people in this room. Height and temperature should be completely independent. If you change the temperature in the room, it doesn't mean that we'll get any taller. Or if taller people get in, it's not going to change the temperature. So it's kind of, these two are independent, but eye and hair color, they are dependent. There's some genes, and there's a statistical probability of something happening. For example, I think a lot of people with blonde hair tend to have blue eyes. And then a lot of people with brown hair tend to have brown eyes. Not blue. Blue is actually pretty like I said, based on the area that that rectangle would do, it just does not work that way. Okay, so how do you actually represent something like that? Like if these were completely independent, it turns out that this representation will be perfectly fine. So what's the solution? Well, the solution is to cut the dependency. What we've done, we drew the lines completely from top to bottom and completely from left to right. What we need to do is kind of cut them like you cut ribbons, and then inside the ribbons you do independently of each other. So we will end up with something like this. Notice here, people with uh, black hair and brown eyes, the cut is right here, but it's not aligned with the cut on the next category. And it's not aligned with the cut on the next category. And you can see how brown eyes and blonde hair is really, really rare. And then you can see this one is actually going a lot higher. That's expressed a lot more in the genes. So there's a lot of dependency right there. So you can do it this way, or we could even do it horizontally, as if I could keep them aligned this way, but then I will have to cut the dependency here. So one row may in this way, the other one may go a little bit higher, depending on what we need to do. So what we need to do is, again, cut it so it doesn't go across on both axes, horizontal and vertical. Once we do that, we have this first idea, first implementation of a mosaic display, and that kind of gives you an idea what you get there. It's not as clear in the sense that if you want to know hazel hair, it's not as clear as moving your eye from left to right. Hazel eyes, I'm sorry. You have to go this way, kind of up and down.
But there the areas represent the number, right?
The area are exactly the number, yes. Because now I can control each individual rectangle. So again, if you look at brown eye and blue, it's just a lot smaller than this one here. Previously, the fact that I kept them aligned, they look about the same, and that's not accurate. So what previously I did not have the choice of setting the area for an individual rectangle here. I had to set it for the entire group, and also for this entire group. So one way or the other, I need to break it, where I kind of cut it and they don't align anymore. They're still, the order is the same. The first one is the first, but they're not going to be at the same level. So that's what you can see here. And you can see that some of them are really small, green eyes and black hair, very, very rare. The same with brown eyes and blonde hair. Seems to be really small. And if you look at the data, it kind of says that it's only 11 people here, and sorry, no, that's this is the data. Only 5 people here, and on the blonde and brown is only 7 people. So it's very, very rare expression of the genes for that to happen. In addition to doing this representation, one other thing they do in mosaic display, just to give you an idea of where things are, they also color it. So the area represents how big that population is, the number. And the other thing they do, they color it based on how far away from this table, from a completely independent table it will be. So in other words, this one here, the blue area, and I'm kind of doing blue and blue, the blue area here is a lot bigger than what you would find in this table. This is completely independent variables. They would look like that. But over here, you can see it, it's a lot bigger. So if it's colored in blue, it means you have that area is a lot bigger than what an independent, what if you want uncorrelated variables would yield. The same with red. This area is a lot smaller than what you would get on uncorrelated variables. Again, that would be brown and blonde. So that was only 5 in reality. So that is a lot smaller than what you would get from here, which is 47. So it's a lot smaller than that. So that kind of tells you how far away from uncorrelated you are. Not all of them are the same degree. So they kind of, you can see here, they tell you how far away the standard residuals are if you do statistics. So how far away from the average, I guess. Well, it's not really average. It's more of a, I forgot about it. It's like an analysis of variation, and you look at sum of squares that are left over. So that's what you normally get here. So you can see that the middle is right here. Then if you have a little bit of deviation on the positive side, then it's just gonna, these are a little bit bigger than what they should be, but they're not a lot bigger. These are a little bit smaller, not quite a lot. And then you get even bigger, even smaller. And then completely kind of blocked color, you can tell they're far away from what they should be. So that's what's causing really the problem. The ones that are not shaded inside, they're close to being independent. The one that's heavily shaded, those are where you have either too many in that area and too little in the next one for it. So that's the whole idea here. I'm using color to kind of give you, for each cluster, how far away are you from two independent variables, and then they're using the areas to tell you how big that is. If you have used R in the past, there is an R package that does that, and it can happen with more than 2 statistic variables like that. In this case, and that's what I found, but it's suicide rates, and they use 3 variables. A big check here is men versus women. Obviously, men tend to commit suicide more. You can see bigger, the lower part is a lot bigger than the upper part. So that's one variable. The other is age group. And you can see that even the age group is separated. It's kind of broken. It's not aligned. And the last one is method, what they're using. One is hanging. I think this is hang, gun. And this I have jumping. And again, looking at the colors, you can see there's a lot. Young people, young male, tend to overuse guns because that's blue. So that area is bigger than what it should be. That's the second one here, hanging, is not very popular with women. Overall, they prefer jumping. So whatever information you get there. So the colors kind of tell you where you have a heavier number than when you have a lighter number that should be. So again, men, especially older ones, don't prefer hanging. They kind of move, they don't prefer jumping. They prefer hanging. They move from guns at the bottom to hanging later in life. It's morbid, I'm sorry, but it's 3. This is an example of 3. You can go to 4 data variable. It gets more confusing as you go higher.